You're good.
I don't know how to do that. I don't know.
Okay, let's get started. So I already sent out the email that had this summary of the grades. The class average was what, a 73, I believe. If I recall correctly, we had 6 A's, 6 B's, 4 C's, 2 D's, and 7 F's. Does that sound right? Yeah. I think I took a picture of it so I could. Yes. We also had a standard deviation of 21 points, which means that the grades were kind of spread out kind of far. So I would just be concerned maybe a little bit, if you didn't pass, maybe come meet with me and sit down and let's go through your exam and let's kind of identify, what the issues might have been. We had perfect scores and we had some low scores, so it's really kind of hard when you have that happen. Like I'd rather have like the entire ship go down, everyone go down with it, or I'd rather have everybody, do well, but it's really tough when you've got a class spread out with the grades. It's just, that's the way it is. So we keep going, right? No matter what, even if you got a 0 on this test, you could still get a B in the class, because remember, it was only worth 15% of your grade. So even if you got 100, you could still get an F, right? So there's still a lot of grade out there to be had. All right? So don't be too demoralized if you didn't do well. Just make sure you do something different. I'm sure y'all have heard the Albert Einstein's definition of insanity. Doing the same thing over and over and expecting a different result. Okay, so if you are doing something, maybe you're doing something that's always worked for you, for all your math classes. You've always done it this way and you've done well, and now you got to Cal 2 and it's not working. That means you need to try something else. I'd also encourage you to try and form groups. All right, and I can't force you to form groups, but I know that there are some students in here that I've talked to already that want to work in groups, just can't seem to find people who are available when they are. So use a discussion board, go in Canvas, The other class, they're all on some app now that they're meeting up, and I don't know.
Like GroupMe?
GroupMe? Yeah, I don't know what that is, but
yeah.
I got added to it, and I get everyone's
Yeah,
message, so I got myself out of there. Okay, but you've got all this technology, this ability to communicate with one another, so I leave that to you, all right? Anything else before we proceed? There are no test corrections. There are not replace your lowest grade with the final, all that stuff. No, it's just this is your grade and find a way through. Now, if you got a 40 on this test and your next exams are all like 97, 98, 100, we may talk, okay? But there's got to be some like night and day thing happening with you, or something happened and there's an obvious difference in what's going on. So. All right, we begin 6.2 today. We will not finish 6.2. 6.2 is a very long section. And fortunately for us, the section is broken into 2 topics. All right, there are 2 concepts here that are connected, but they are separate enough that we can treat them as 2 different things. The first part that we cover today is called Trigonometric Integrals. And then the second part is known as trigonometric substitutions. In order to do trigonometric substitutions, guess what? You have to be able to do trigonometric integrals. So we have to master this before we can start doing this. All right? So here we go. I'm going to make this a little bigger so you can see this. Oh, also on your desk you should have a new calendar. Make sure you take a copy of this. The calendar that's up on Canvas was the same calendar, but it did not have all the homework assignments for all the sections. So this does, and you can follow this the rest of the way. I even 3-hole punched it for you. How about that? Okay. 6.2, trigonometric integrals. So what are some things we already know? Well, we already know the antiderivative of sine x is negative cosine x. We know antiderivative of cosine x is sine x, right? Plus c. Further, we established these formulas that were useful on that test. This did come up a few times, where if you have sine of a linear expression, then the antiderivative is negative 1 over a cosine ax plus c. And then same thing with cosine, you get a 1 over a out there, right? We've done that? Yeah. So that we know. So we can do some integrals that involve trig, right? These are 4 examples of trigonometric integrals, integrals with trig functions, okay? But now we start to expand out what these things look like. They're going to get more complicated now. And we do have a general strategy, okay? There is a strategy. It's not like a cookie cutter technique you use every time, but it's a strategy that we employ whenever we're trying to attack a trigonometric integral. So the first thing we do is we say, all right, what if our integral has just sines and cosines in it? Nothing else. Sines and cosines. There's no tangents in there, there's no logarithms, there's no exponential functions, just sines and cosines. Then we have the following strategy. Now this, we can read this and you're going to sit there going, what the hell are they talking about? So I think what's better is for me to do an example and then kind of refer back to the strategy and say, hey, look, this is what we did. All right, so I'm going to just go to an example. So let's look at that first one. Sine cubed of 4t dt. And notice I'm using t instead of x, right? I'm going to have to give me a second to get a blank screen up here. Well, that's the solutions to your test. Okay, here we go. So do you remember we did the reduction formula? Sine to the n? We could use that here if we had the formula. But on a test, you are not allowed to have that reduction formula. Okay, so that's off the table. So let's try and do this without the reduction formula. So it's a trig integral, right? We see sine in here and just sine, so it's trig integral. And we see that there is an odd number of sine factors, right? Sine cubed. So what we can do is first eliminate all the other techniques. So there's no basic substitution. There's no integration by parts here. Now, how do we know that? Well, that's why we took an exam over those things. We kind of need to be at that point now where we can look at this and recognize that we don't have, the other techniques we have aren't going to work here. So that moves us to the trig integral strategy, which is to do the following. If we have an odd number of factors, then what we will do is we will peel off, let me do it this way. I'll do the square first. We are going to peel off one factor of the sine of 4t. So that's still sine cubed, isn't it? Sine squared times sine. All right. And then what we're going to do is we're going to take this, we're going to have an even factor, right? So if this starts out odd and we peel one factor off, then we're guaranteed that this one's going to be even now, right? And if that's even, then we can use the Pythagorean identity, which I'll remind you of the Pythagorean identity. Sine squared x plus cosine squared x equals 1, right? So if I solve this for cosine squared, this would come over. If I solve this for sine squared, the cosine comes over, right? So what I'm going to do is I'm going to replace the even one right here with something with cosine in it. And what does it become? 1 minus cosine squared of what? 4t. Okay? So that's the Pythagorean identity, right? Agree? Okay. Then I still have sine 4t dt. Now let's think about this strategy. We had nothing but sines, right? We peeled one sine off. With the even power of sine, we went to cosines, right? We switched from sines to cosines. Why? Why would we want to switch part of our integral to cosines and leave the sine out here? Not cancel. We can make a substitution now, a basic substitution, where u will be, well, either sine or cosine, right? But which one? Which one should we use? If we're going to do a basic substitution now, what should we use for u? We could do, okay, so let's run through. If we did sine, right, as u, the derivative of that is what? Cosine? And it would be trapped in here, wouldn't it? Now, I could try and grab the whole thing. 1 minus cosine squared 4t is my u. But the derivative of that is complicated, isn't it? Because you would have chain rule and stuff. So why don't we just grab the cosine? Just the cosine of 4t. Let's let that be the u. So I'm going to do a basic substitution now. U is going to be just cosine of 4t. Go with me? Now, how do we know its derivative is out there? Well, because if you have an odd number of sines, you peel off one sine. That sine right there is always the derivative of the cosine, right? So the derivative of this is what? Negative 4 sine 4t. Why is it not 1/4? We're taking the derivative. We're not integrating, right? We're not integrating that. We're differentiating that. So we have derivative cosine of something is negative sine, and then derivative inside is 4. So that's what we got, right? And do we see this in our integral? Yeah, I see the sine 4t dt, right? There it is right there. I'm off by a factor of negative 4. So I just scale both sides. Negative 1/4 du equals sine 4t dt. So now I have something I can replace with, right? This is good. And now I just need to rewrite the rest of the integral. And I can replace the guess that one's dead, huh? All right, whatever. You have a red one? There a red one or anything? No? Throw them this way. Fire away. Go ahead. Just don't hit any. Blue, I'll take blue. I'll take red. Yeah. I've been doing this for a while.
Baseball story.
Okay. So that is just going to be the cosine 4t, right? So now we rewrite the integral, right? We rewrite the integral. So this becomes integral, let's see. Let's do this. 1 minus what? U squared, right? That's u squared. And then I'm rewriting all this stuff in blue here as negative 1/4 du. And I'm going to pop the negative 1/4 onto the outside. I should have given myself enough room there. Negative 1/4 comes out in du. And look at that right there. You can do those each individually, can't you? You can just antiderivative of 1, antiderivative of u squared, and we're in business. So really, this part is stuff we've done, yes? The only true new thing right now is the fact that we peeled the sine off, used the Pythagorean identity to rewrite that in terms of cosine, and then used the basic substitution. Yes? Okay. Let's finish it. We are getting to a point here, not yet, but where I will get to a point in a problem where I will just stop and I will say, and then you could take it from there, all right? Because we just won't have enough time to go all the way with it. Okay, so negative 1/4 comes out here, and now I've taken the antiderivative, so let's do it. Antiderivative of 1 is u, right? Because our variable is u here. Then minus 1/3 u cubed. and then plus some constant. And substitute u back in, and so this becomes, and let's go ahead and distribute the negative 1/4 through also. So negative 1/4 u, which was cosine of 4t, and then plus 1/12, because you're multiplying negative 1/4 times negative 1/3. And then I'm going to square cosine, right? So cosine squared 4t plus some constant. There it is. Did I cube it? Did I not cube it? I was supposed to cube that. Thank you. Thank you. Just making sure you're paying attention. Everything else is good, right? All right, that's it. If we take the derivative of this, we should get, we'll actually get like this. And then we can use Pythagorean identity to go backwards. So if you take derivative of that right now, it's not going to look like sine cubed 4t. You're going to have to like do stuff first. All right, that worked, right? So now let me go back and bring up the notes. And I think these instructions will make a little more sense now. Actually, the one we just did was this strategy right here. The strategy said, if you have sine raised to the n, with n being odd, then use Pythagorean identity and factor out a single sine, which leaves an even power of sine. That's what happened, right? Now rewrite the remaining even power of sine using the fact that sine squared x is 1 minus cosine squared x. Does that make more sense now? And then make the substitution u is equal to cosine x, because then its derivative is sine x is there. I think if I read that out in the beginning, you'd be like, what? At least I would. Okay. Now, that's what you do if you have sine to an odd power. What would happen if we had cosine to an odd power? Well, let's see. What would you do? If you have cosine to an odd power, then use a Pythagorean identity again. This time, factor out a single factor of cosine. Rewrite the even power of cosine using the identity to switch it to sines. Let u be sine, and then its derivative cosine would be there, the one that you pulled out. So it's kind of reverse of what we just did. Let's do one. I don't think I'll take it the whole way. I'll just get it set up. How about that? What if we do this? Cosine to the 7th, and let's do pi x dx. So we have an odd power of cosine, right? So I will peel off what? I'm going to peel off a single factor of cosine. So cosine pi x out here, like that. Cosine to the 6th, but wait a minute, the Pythagorean identity is sine squared x plus cosine squared x equals 1. We can't just change these to 6's, right? It doesn't work that way. So I could write cosine squared x is 1 minus sine squared x. That's about the best I can do. Yeah, but isn't cosine to the 6th cosine squared cubed? Isn't it? So this is cosine squared of pi x, that quantity cubed. We agree? And the cosine squared pi x can be rewritten as 1 minus sine squared pi x. Yeah? So this would be, let's see, 1 minus sine squared pi x to the 3rd. cosine pi x dx. Y'all see what I did there? Just rewrite 6 power is squared cubed, and then rewrote the squared cosine as 1 minus sine squared, and then cubed that. And then I've got my little cosine sitting out here. So now at this point, let's see if we can try the substitution. What's the substitution going to be? U is this time sine pi x, right? And the derivative of that is pi cosine pi x dx. Little chain rule there, popped out the pi. Do we want that pi? We don't have that pi over here, do we? So let's just scale it out. So how about we divide both sides by pi? So we've got our cosine pi x dx right there. That's taken care of. And then we have our u is this piece right here, which is just that right there. Good? Let's rewrite that. The new integral is what? So integral 1 minus u squared, but then all of that cubed. Don't forget the cubed. And then all of this is 1 over pi, which I'll put on the outside, du. Agreed? Ooh. Ooh. What in the world do we do with that? I don't see a basic u sub here. I don't see like something in its derivative. I'm trying to figure out how are we going to integrate this, right? Like integration by parts. How about we just cube that binomial? Why don't we just expand it out? Why don't we just do 1 minus u squared times 1 minus u squared times 1 minus u squared? No? You don't want to? Why? I think it's, well, because how else are you going to integrate that? You can no longer integrate these individually because of the cubed. So that would work, right? That would work if I could get these into single terms.
What would we do if it was like 79?
You would get very upset at me for giving you a problem that had 79th power. And that would probably fall more into, hey, that's where you would definitely want to use the reduction formula. But even that you would have to do it like 78 times. So there's no easy way around higher powers, okay? I think it's safe to say, though, that no matter what this power is, with this substitution, we get this to a polynomial, right, that we can expand and just do term by term. Now, you may not want to expand this, but it can be done. So I'm going to expand it. And that's where I'm going to stop, and I'm going to let you take it the rest of the way. So how do we expand that? Yeah, so don't worry about me giving you anything higher than 7th power. I wouldn't do anything like that. All right? We do 1 minus u squared times 1 minus u squared times 1 minus u squared. That's what I'm doing, right? So this all depends on you. I mean, there's shortcuts. There's formulas for doing cubic, like binomials, cubed, and all this stuff. But, you know, if you're hard-pressed to do it, just put those two together first. So what are those two together? 1. That's those two combined together. And then you distribute here, 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 and then here, here, here. So we're going to have 6 terms. So we're going to have 1 minus 2u squared plus u to the 4th minus u squared plus 2u to the 4th minus u to the 6th. And then I collect all my like terms together. So my new integral is 1. How many u squareds we got? Not too sure what? You have a question?
No.
Okay. So I just collected my u squareds and my u to the 4ths together. And that should be it, right? Now we would need to take the antiderivative. So the antiderivative, we'd have a 1 over pi out here. The antiderivative of this would be u. Antiderivative of this would be, so minus, just u cubed. The antiderivative of this would be 3/5 u to the 5th. The antiderivative of this would be minus 1/7 u to the 7th, right? And we have a 1 over pi out in front of everything. Plus c, replace u with sine of pi x. So you could take it the rest, you think? Yeah? Okay. All right, so we have a method. We have a method in place now if we have sine to an odd power or cosine to an odd power, right? It seems like this will get us there no matter what. Y'all ready for spring break? Wait a minute, wrong semester, right? I'm just messing with you. Just messing with you. Look at the next one. Sine squared cosine to the 5th. What? Sine squared cosine to the 5th. Sine squared x cosine to the 5th x dx. All right, so I haven't talked about what we do here. We know what to do if we have sine to an odd power by itself. We know what to do if we have cosine to an odd power by itself, right? We've talked nothing about what if we have both sines and cosines mixed together. So if you tried right now, just a basic substitution, if you let u be sine x, that seem reasonable to you? Don't write this down. Does that seem reasonable to you? Then this would be u squared, right? But this is not du because it's to the 5th power, right? So you would have that derivative trapped. So that doesn't appear that that would work. Also, if you do cosine x, the derivative of that is sine x, right? And that sine is being squared, so again, it's trapped. Does that make sense? Yeah. Okay. However, we can still do it. And it's going to be one of those substitutions, but let's try and logically think about how we might be able to do it. So anybody have an idea of how we might go about this? So if we replace this sine squared with 1 minus cosine squared, then we're going to have all cosines, right? And we could probably do that. Let me again, don't write this down, okay? This is what we would have if we replaced our sine squared with 1 minus cosine squared, yes? Yeah. And then if I distributed this here and here, the first one would be cosine to the 5th power, and then minus we'd have cosine to the 7th. And we know how to deal with cosine to odd powers. Right. So we could do those individually, couldn't we? Yeah. That would work, but it's a longer road to the same destination that we can get to shorter, with a shorter path. So that would work, but it's not recommended. All right? Someone else have an idea? So let me show you what you should do, and then I want you to think about why. And maybe you were thinking about this, but you just didn't quite have the nerve to say it. Is that what you were thinking?
Yeah, we're going to use identity twice, right?
We're gonna use an identity. I don't know if we'll even need it twice. Let's see. If I peel off one cosine, right? Because this cosine was odd, wasn't it? If I peel off one cosine, then this cosine x dx, I'm imagining, is going to be my du, all right? Which forces my substitution of u to be what? Sine. So this right here is nice, right? What's that for us if we make that substitution? U squared. But see, this is not, you are not going to say, well, that's du to the 4th power, right? This is du right here, right? So this right here is good. This right here, right, is good. This is the only part right here that we need to still resolve. So how can I resolve that? the Pythagorean identity. It's cosine to the fourth, right? Which is the same as cosine squared squared, which is the same as 1 minus sine squared x squared. Isn't that what that is? So I'm able to rewrite the cosine to the fourth x in terms of sine, which is my u. So let me rewrite it. Integral, I have sine squared x out front. This cosine square, or cosine of the fourth becomes 1 minus sine squared, but all of that quantity squared, and then I still have cosine x dx. Okay? Now let's just make the substitution. This should turn out to be a nice little polynomial here. It is integral. This is u squared, and then parentheses, this is 1 minus u squared squared, and then this is exactly du. Now you may not want to deal with this, but you have to. Okay, we have to expand this, because if I square that, I'm going to get a polynomial. Then I'm going to distribute the u squared through. And I'm going to have a bunch of u's raised to different powers. A bunch. I'm going to have how many? 3? Any questions on this? Do you all follow what I'm trying to accomplish here? I'll go 2 more steps. Okay, that's me expanding this right here. And then I won't do any more. The next one, this one goes through, right? And now you'll have a bunch of things used to powers, and then you can do the power rule. Okay. So how about from here I just say ... Questions, comments, concerns, complaints, gripes? Anyone just want to yell? No. I'm curious, if somebody can tell me, if we do this problem, if we rethink it again, can somebody tell me why this would not be a smart move? Why would that have not been a smart move? Like, I had originally peeled one cosine off, right? Why not peel off one sine? What do you think?
Because you'd have like 1 extra sign left.
I have a sine left. Yes, I do have a sine left. Why is that bad? Yeah, that's right. I don't have sine squared. And the Pythagorean identity is relying on having squared things, right? Cosine squared can be replaced with 1 minus sine squared. Sine squared can be replaced with 1 minus cosine squared. But sine by itself cannot be replaced with like 1 minus cosine, right? So we don't have an easy way. See, if we are going to let the sine be our du, then that means u has to be cosine, doesn't it? That means everything over here needs to be turned into a cosine. That's fine. This can't be turned into a cosine, though. There's not an easy way to switch from sine to cosine unless it's squared. Make sense? Okay. So let's see if maybe the strategies will kind of become a little clearer now with what you do in... I keep on pressing the wrong thing. Go back up to the strategies. No. Well, the way you can read this strategy is this. If you got cosine to an odd power, we peel off a cosine, right? If you have sine to an odd, you peel off a sine. In the previous problem that we did, we had a cosine to an odd, right? So we peeled off a cosine. Okay? What if they would have both been odd?
You can still peel one off
You could peel one off?
because they're almost times each other, right?
Yeah, so what would happen here? Let's not go through the whole thing, but we could peel one off. But which one do we peel off, sine or cosine?
Both.
If you peel them both off, then you've got over here sine times cosine, right? Which would have to be your du. And that means what would u be? You know what I'm saying? It turns out you could do it either way. Okay? You could peel a cosine off here and work it out, or you could peel off a sine. Either one. Do you want to see how that would work? Let's say, so I'm going to look at two different options here. I'm going to set up both problems. I'm going to set up this problem two different ways. Because they're both odd, it does not matter which one you peel. Now, if only one of them is odd, you're going to peel off the one off the odd one, all right? So let's look at option one. Let's let this be sine cubed x cosine to the fourth x cosine x dx. Right? That's one option. The other option would be to go sine squared x cosine to the fifth x. I peeled off a sine x dx. So y'all agree that would be my two approaches? Okay, in this one, what would u be here? Sine, because we're going to try and get cosine x dx to be our du. So this means this is sine x, du would be cosine x dx. Over here, what would our u be? Negative cosine of x, because du, or we could just do cosine. Let's do cosine, all right? Then this is negative sine x dx, and we're off by a constant, right? So I just make that minus and that plus. So those are the two different ways you could do this. Now on this one here, this would be rewritten as integral, then what? U cubed. But then the cosine to the fourth has to be rewritten. So that's going to be 1 minus u squared squared. Because u is sine, right? So this is 1 minus sine squared x, but then that whole thing squared. And then du. How would this one look if we did this problem? Here, we can leave the cosine as our u, right? So we need to rewrite this. This would become 1 minus cosine squared, and cosine is u, so that would be 1 minus u squared, u to the fifth, and then du, but then a negative out there.
Would it matter if you use negative cosine? Because
You could use negative up here to make it match. You would still get a negative because it's to the fifth power, so you'd still get a negative on the outside. I hope that makes sense. The moral of the story is this. If you see sine by itself, to an odd, peel off one sine. Cosine by itself, to an odd, peel off cosine. If you see sines and cosines mixed, and one of them is odd, you peel off the odd one, right? If they're both odd, doesn't matter which one you peel off. So what do you think is coming next? Even, right? What if you got evens? And this is where things start to get tedious. You want to talk about tedious problems? You're about to see a tedious problem right here. Things start to really get nasty fast here, all right? So let's put the problem up first. We'll start with this one. Sine squared x dx. And then before I begin, I'm going to remind you about a formula you had from pre-cal. Actually, I'll write two of them down here. See if this looks familiar to you. Sine squared x equals 1 minus cosine 2x over 2. And then there was another one, cosine squared x equals 1 plus cosine 2x over 2. These are on your formula sheets, I hope. You can double check for me, please. Power reducing. I don't think they call them power reducing formulas. Here, can I look at yours real quick? Thank you. This would be on the pre-cal formulas. And they are there. They call them the half-angle formulas. Reference page 2, bottom right-hand corner. They call them the half-angle identities or half-angle formulas. I don't like that name. I like the name power reducing because what do? They take a sine squared and they turn it into a brand new expression. It has cosine in it, right? But that cosine's not squared anymore. So you've reduced the power, haven't you? But there's always a give and take in math. If you want to reduce the power, what changes? I mean, it goes to a cosine, obviously, but what else changes? The argument goes to 2x. It goes from x to 2x. So it's kind of like this formula is saying to you, look, I'm willing to allow you to take the power on that thing down, but you're going to have to double the argument in order for that to happen, and then, you know, put it into this nasty little thing. All right? So there's a give and a take. Now, because we are going to be doing integration, I don't like the formulas written like this. I prefer to have this formula written this way. 1/2 minus 1/2 cosine 2x. Do you all agree that that's just splitting it into two fractions? And if you want, you could even go further and pull the 1/2 completely out and rewrite as 1 minus cosine 2x. Right? That's the same thing, isn't it? I like this one because we already know what we're going to do with any constant in an integral, right? It's going to come out, and then this is just two terms. I can do them term by term, integration. Yes? And this formula, same thing. This turns out to be 1/2 1 plus cosine 2x. Both of these formulas have cosine in them, okay? This is not a typo, all right? Sine squared x turns into some sort of cosine in it, but you have subtraction here. Cosine squared x comes into this thing, but it becomes a plus, right? So that's the big difference between the formulas, that minus and that plus. All right, so let's take a look at this one over here. Do you understand why we can't use the method we were using with odd power? If we peel off a sine, let's say we were trying to be all clever, right? Let's say we peel off a sine, then this right here would be our du, right? That means u would have to be a cosine, wouldn't it? And you cannot turn sine into a cosine. You can't, right? We don't have a formula to go from sine to cosine. Not a nice one. So I can't do anything. Now, if this was sine squared, I could, right? But then that would have been sine cubed, and we already know how to do that. So this problem, the only way to get through it is to use this power reducing formula. So all I'm going to do, look at this, say, that's an even power of sine. So this is going to become 1/2 1 minus cosine 2x dx. That's just this, right? And then you integrate each one. So 1/2, here we go. Antiderivative of 1 is x minus antiderivative of cosine of 2x is 1/2 sine 2x. Where did that 1/2 come from? Yeah, when we go backwards, right? When we go backwards on cosine, we got to do 1 over a sine of ax or whatever. Yes? Which one? The one where you divide by a? Yes. That one? Write it in here. Just burn it in. It happens so often from here on out that you don't want to be like, what was that formula again? I mean, it's almost like the Pythagorean identity just needs to be in there. Okay, plus c. And then this is 1/2 x minus 1/4 sine 2x plus c. And come on, you've got to be saying to yourself that there's no way that the derivative of that is sine squared x. No? Yeah. No, we don't care. You believe it? Do you believe it? Yes? I'll tell you real quick. If you took the derivative of this, you get what? 1/2? If you take derivative of sine of 2x, you get cosine 2x times 2. Yeah? I'm going to just write it down. 1/2 minus 1/4 cosine 2x times 2, and then that 2 and 1/4, this would just become a 1/2, right? That's where we are? That would be the derivative. How is that sine squared? Pull the 1/2 out, right? And you're there, right? That's it. But I was trying to make it that way without this formula. If you there's a formula on your formula sheets for that called a double angle identity, and you can use that double angle identity right in there, and it'll get back to sine, but sine squared. All right. I told you this is where things become tedious, right? That didn't seem very tedious. Let's change it to cosine, just for fun. And let's just go to the 4th power. We have an even power of cosine, right? This formula allows us to reduce the power from squared down to cosine to the 1st power, right? But this formula does not say that if you replace that with 4 that this becomes squared. That it only goes from squared down to this, right? So here's what we have to do. We have to first recognize that that's cosine squared x squared. So that seems to be something we've done before, right? Nothing crazy there. But what's cosine squared x with this formula? This, right? Okay, so this integral becomes 1/2 times 1 plus cosine 2x, right? That's this piece right here, but then all of that squared again, right? And now we're squaring 1/2 times this, right? So when you square multiplication, you can square each one, can't I? Right? If I say, take x times y and square it, that's x squared, y squared, so long as that's multiplication. Right. So I can square the 1/2, so that 1/2 becomes 1/4. And then I can square this, right? Which is 1 plus cosine 2x squared. Can I pull the 1/4 out? Yes. So this is 1/4 integral 1 plus cosine 2x, but that whole quantity squared. All right. That looks very similar to the last problem, right? Like we got it down to like 1 plus, or it was 1 minus cosine 2x. But we didn't have the square, did we? Yeah. So guess what we get to do? We get to square it. We get to square it. And that means we need to multiply it times itself. So this becomes 1/4 integral. And now when you square that, I'm going to put it down here, okay, just so you can see what I'm doing mechanically. Okay, I'm going to do a FOIL here, our favorite word here. Favorite. 1 times 1? 1. Okay, 1 times cosine of 2x, cosine of 2x. Cosine of 2x times 1, cosine of 2x. So we have 2 of them, don't we? So we have plus 2 cosine of 2x's. And then what's your last term? Very important, the last term. It's cosine of 2x times itself, so it's squared. So it's cosine squared of 2x dx. Yeah? Now, we've separated this into three terms, haven't we? No more squared out here, so we can look at them individually. Can you take the antiderivative of 1? Yes. Can you take the antiderivative of cosine 2x? This is the formula you're going to burn into your brain, right? That one? Yes, we can handle that. Can you do it with cosine to an even power? Yes, we got to do everything we just did again. See, because that's a squared, right? I need to power reduce that. So that's going to be its own little animal that I'm going to have to deal with. Understand? Let's do it. We're not done, so continuing this train of thought, here's what I've got. 1/4. I'm going to break this up. I don't normally do this, but I'm going to break it up. 1 dx plus 1/4 times 2 integral cosine 2x dx, and then plus 1/4 integral of cosine squared 2x. Don't mess that up. 2x dx. So what I've done is basically I've split this into three separate integrals, right? With the 1, the 2 cosine 2x, and the cosine squared 2x, and I just put the 1/4 in front of all of them, right? And I pulled this 2 in front there. That okay? So that's me doing them individually, but actually writing it down on paper. So here comes. Some of these are easy, some of them are going to require more work. This, 1/4 x, right? All right, this is a 1/2, isn't it? 1/2. And now what's the antiderivative of cosine of 2x? Oh, shh. Let's see. Antiderivative of cosine 2x. Okay, 1/2. Antiderivative of cosine. So 1/2 sine 2x. There you go. See, you got it already. So we already had a 1/2 out here, right? From this, we get another 1/2 sine 2x. We're 2/3 of the way through the integral, right? We've got 2 of the 3 integrals done. Plus 1/4. This integral I'm not ready to do yet. I need to use the power reducing formula for this one. So the formula says that I can, are y'all understanding what I mean by that? This needs to be rewritten using our formula.
So the power will be down.
The power is going to come down. So the formula is 1/2, then in parentheses, well, let me write the formula again. Cosine squared x equals 1/2, and then 1 minus, plus cosine of 2x, right? That was the formula? Yep. I said you can bring the power down, but you got to double the argument, right? Yes? Yep. What's the argument here? 2x. So when we double it, it's going to become 4x. So this becomes 1 plus cosine 4x. We're doubling the argument. Let me just write the next line. 1/4 x, nothing changed. This one, 1/2 and 1/2 is 1/4, sine 2x. This one's going to become plus 1/8 integral, because I pulled the 1/2 out with the 1/4. And now I'm ready to integrate these little guys. I'm going to tell y'all something. I'm going to mute my microphone because I probably get in trouble for this. All right, let's keep going. What do we got? This equals 1/4 x. It's sad that I have to mute my microphone to say something like that. You know, it's 2018. I don't know what's going on. Okay, here we go. X plus 1/4. Where did that 1/4 come from? Yeah, that 1 over a, right? Sine of 4x plus c. There we go. So that's it. That's the antiderivative of that. And we are close. Not quite there. We're almost there. I said tedious, right? I think I've delivered again. I continue to deliver my promises. Can't see? Move the table, like y'all slide down or something, man. Seriously. Oh, I screwed that up. Okay, hold on. I almost screwed that up. Okay, so I have this 1/8. I got to distribute the 1/8 through, right? So that's going to be 1/8 x, but then 1 over 32. 1/32 sine of 4x plus c. Yeah. That any better that way or what? Still bad?
But do you want to take out the 1/4 and just leave it?
Do I want you to take out the 1/4?
In the whole thing, just
Oh, like to pull a 1/4 out of everything? Not necessary.
Okay.
But there is one thing that you should do, and that's combine these like terms together. Most students forget to go do that part. It's not wrong, okay? This is correct. But, I mean, you do have 1/4 x plus 1/8 x, which is 3/8 x. So you can put those together, and that would be a final nice clean answer, like 3/8 x plus 1/4 sine 2x plus 1/32 sine 4x plus c. Man, that got really complicated really fast, right? Not complicated, but tedious, right? Can you imagine what this would look like if that was cosine to the 6th power? This would be cosine squared cubed, right? So when we turn that into that thing, we cube it, we're going to have lots of stuff. Let's look at it. Yeah, but let's look at it for sine. Look, every Cal 2 student has to see sine to the 6th or cosine to the 6th. It's part of like, it's a ritual. It's like a rite of passage, all right? You've got to see just how tremendously nasty this stuff gets fast. Sine to the 6th x dx. I'm not going to take this the whole way, all right? So first thing, I look, it's even. Okay, if it's even, I need a power reducing formula. So I'm going to go sine squared x. I'm going to cube that. I don't know why I did equals, dx. And then I rewrite sine using its formula, which is going to be 1/2 1 minus cosine 2x. That's the formula for sine squared x. But then I'm cubing that, right? Cubing the whole thing. Sorry. Cubing the whole thing. That includes the 1/2, right? That 1/2 gets cubed also. Any questions up to that point? Okay, now let's cube. So we have, when we cube the 1/2, it becomes